Okay, good morning, everyone. Just a couple of announcements up first. Quiz is going to be tomorrow, but I'm breaking up chapter 4, logic circuits, into two parts. It'll be a quiz tomorrow based on the first half of chapter 4, which is the binary number system, the fundamentals, the Boolean algebra. Well, actually, maybe not Boolean algebra, but mostly the binary number system, the ones complement, two's complement, and adding or subtracting two binary numbers. So converting from decimal to binary, binary to decimal, and adding and subtracting binary numbers. So that'll be the first quiz. That'll be tomorrow. Thursday, I'll open it up at 8 o'clock in the morning, available to students till 12 o'clock at night. And the second portion of the second quiz based on the second half of this chapter will be on Monday. So I will give students the weekend to get caught up on the homework, study, get your questions answered, and then Monday we'll take that quiz. Okay. All right. So for now, let's continue with flip-flops. So we stopped here last class and we introduced the concept of an edge trigger. Remember, we talked about clock to keep everything synchronized, right? We talked about clocks to keep everything synchronized, which is shown in this circuit diagram, in this figure. A clock signal is basically a square or rectangular pulse that is on and off. If it's on, we say it's logic high, it represents 1. If it's low, it's 0, then logic low. But now, let's take it one step further and explain the edge trigger. So oftentimes there are circuits that will respond to a value of logic 1 or logic 0. Now, depending on the clock frequency, the clock signal value will stay high, meaning at 5 volts for a certain period of time. And sometimes that interferes with the operation of the circuit. So designers and engineers came up with a way where the circuit would not respond to the actual value of the clock signal, but instead it would respond to the change in value. Okay. And that's where the edge trigger comes from. We have two edges in a normal square wave signal. Once when the value goes from low to high, and so this is, as I pointed out and stated last class, is known as a rising edge. It's going from a lower value to a higher value, so it's attaining a positive value. So it's also known as a positive going edge. Okay, positive edge. And the other side, of course, is when the value comes back down from high to low. The value of the signal is going in a negative direction. Hence, it is also known as a negative going edge, but more commonly known as a rise and a fall. A rise and a fall. So rising edge and falling edge. And so circuits are designed to respond to the change in value of the clock signal. Change in value, not the value itself. Okay, it's designed to respond to the change in value, not simply the value itself. And again, this is important because these are applied to sequential circuits. Sequential circuits, meaning there is a sequence of operations that take place, and the system will have multiple components. So each component, the input to each component depends on the output of the previous component. Okay. So all the components in that system respond in a sequential manner. They respond in a certain sequence. All right, questions? Any questions about clock, edge triggered, positive edge triggered, negative edge triggered? Okay. The notation of a clock signal is given like this. It's an arrowhead inside the circuit diagram or the diagram. Okay. And this is used to note a positive edge. A positive edge. It's used to note a positive edge. If you take the exact same symbol and you place a small bubble or a circle on the outside, it indicates a negative edge. A negative edge. So when you're trying to read a timing diagram, or if you're trying to write a timing diagram or create a timing diagram, these are of utmost importance. Okay, because your timing diagram would be completely incorrect if we do not take either the positive or the negative edge into account. All right, questions? Okay, then let's look at the first flip-flop based on this edge triggering. What do we notice at first? There is a clock signal, and the clock signal, because it has a knife's edge, the arrowhead, is a positive edge triggered signal. It's a positive edge triggered flip-flop. Positive edge trigger. Same standard outputs, Q and Q naught, and only one input. Now, again, if you think back to the beginning, I said flip-flops are considered to be like a sealed box, right? We're taking the input, we look at the output. So we are not concerned with what is inside that box. We only need to know what the flip-flop does, okay? We are not, at this moment in this class, we are not concerned with how it does it. Okay, so we're not looking at a circuit diagram. You're looking at a flip-flop as a building block of a larger system. So the D flip-flop simply stands for delay. That's all it is, delay. And all it does is it takes the input and provides it to the output or sends it to the output. Okay, so Q is simply equal to D and Q naught is simply equal to D naught. That's it. Q is equal to D and Q naught is equal to D naught. That's it. And what it does is it simply takes the input at D. Doesn't matter what value D has, it sends it to the output after a certain period of time, hence the word delay. Okay, the word delay is due to the fact that after a certain delay in time, after a set period in time, it sends the value of D to the output Q. And that delay is controlled by the clock input. So if we have a clock input that looks like this, if this is the clock signal, the flip-flop that is shown in the illustration here, for every positive edge, meaning here, here, and here, will send the value of D to the output. Okay, so it doesn't matter what the input is. At each one of these positive going edges, send D to Q. Hence the truth table. You have a rising edge, and at every rising edge, the D value is sent to the output. 2 up arrows, 0 and 1. At the output, you get 0 and 1. For all other values of the clock input or the clock signal, it doesn't matter what the input is. And that is illustrated by these X's. X indicates don't care. Doesn't matter. Don't care. It's literally known as a don't care state. So the technical name for that X is don't care. But in simplest of terms, it's irrelevant. And again, that is because the circuit is designed, the flip-flop is designed to respond only to the rising edge at that clock input. If it's not a rising edge, meaning if the value is either constant 1 or the value is constant 0, or if it's the falling edge, the circuit, the flip-flop will not respond. Hence, don't care. So the clock is 0 or the clock is 1. It doesn't matter what the input is at D. The outputs remain constant, previous state. Q n minus 1, which indicates the previous state. If Q was 1 and clock was 1, it'll stay at 1. If Q was 0 and clock was 1, output would still stay at 0. Okay? So again, doesn't matter what value the clock has, the flip-flop is not going to work. Well, it's not going to change the output. It will remain in its previous state. Let's take a pause, think over that, and let me know if you have any questions. Does that make sense? Okay. Any questions from anyone? Okay, well, let's look at an example then. We have to create a timing diagram for the output of a D flip-flop. Okay, so now timing diagram means it shows the input, the clock, and the output. So when I say create a timing diagram, well, the clock and the D input is already given to us. The only thing we need to complete is the output Q. So create a timing diagram in this sense means what is Q output? So for the D flip-flop, that is, well, actually it's not shown, but for a D flip-flop. So for a D flip-flop, this means determine and draw Q. Okay, determine and draw Q. So let me draw it right below. Let's see. Okay, that's about as straight as it gets. This is T, of course, time on the x-axis. and this is Q. Okay, so 1, oh, not 1. 1, 2, 3, 4, 5, 6, 7, 9, 11, 13, 15, and 17. Okay, so 3, 2, 1, and not quite 4, 5, 6, and 7. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15, 16, and 17. Probably a little bit off, but let's here's the point. So I typically, what I like to do is, it doesn't matter what values are provided in the problem, I like to, draw out all the values. So in this case, 2, 4, 6 even numbers are provided. I like to draw all of them out just because D has odd numbers. So if this is a positive edge trigger, then we have to count or mark the positive edges, right? We have to mark and count the positive edge. If it is a negative edge trigger, then we have to note the negative edges. Okay, negative edges. So right now, nothing is stated in the problem. If nothing is stated, you make your own assumption. Let's say, okay, I'm going to draw the timing diagram. I'll assume it's a positive edge trigger flip-flop and proceed from there. Okay, if it's not given, if it's not specified, you assume either positive or negative and work your problem. Typically, the edge trigger flip-flop or edge trigger timing diagram would always have or would always state either the positive edge or the negative edge. So in this case, let us assume positive edge trigger flip-flop and note all the positive edges. So you got 1, 2, 3, 4, 5. At 0, 4, 8, 12, and 16. Right? 0, 4, 8, 12, and 16. So let's take a look. If it's a positive edge trigger, the D flip-flop will send the D value to the output. Okay? At the first positive edge, which is at T equal to 0. So positive edges are at T equals to 0, 4, 8, 12, and 16. What are the values of D? What are the values of D? At 0, the value of D is 0. At 4, the value of D is 1. At 8, the value of D is 0 again. At 12, the value of D is 1. And at 16, the value of D is 0. For all other cases, meaning for a negative edge, for the clock being 1, for the clock being 0, the output Q will remain in the previous state. So if you were to draw this, for T equal to 0, D is equal to 0, at T is equal to 4, D is 1. So the output Q will not change until T is equal to 4. Because at T is equal to 0, D is equal to 0. And I'm going to use a different color for this. Let's use, well, I'll stick with blue. So output remains 0 until 4. Because at T is equal to 0, D was 0. Q is simply 0. Even though D value has changed from 0 to 1 at 3, right? It's gone 0 to 1 at 3. nothing changes at the output until the next positive edge trigger arrives. So the output doesn't change until t is equal to 4. Does everyone see that? Right? So at t is equal to 4, output goes high. And it remains high until the next positive edge trigger arrives. At 8, D has a value of 0. And so output Q goes to 0. And then it stays 0 until the next positive edge arrives at 12, and the output goes high. Okay. And at 12, it remains high until (16) when then it goes to 0. Okay, let's take a 10-second pause, maybe longer. Write it down, think over it. Let me know if you have any questions. Does it make sense to everyone? Any questions? Okay, well, then let's take a look at the next one, which is JK. JK flip-flops. Now, if you recall, for the SR flip-flop, we had a state where both inputs, S and R, would be high. Let's bring that back up here. Okay. S and R would both be high, and that state is not allowed because the flip-flop output would be unpredictable. It would be a race between both inputs to see which one reaches first. So if R is high and S is high, what does it mean? R and S stand for reset and set. If R is high, output is 0. If set is high, output is 1. If both are high, then it's unpredictable. The circuit, again, responds in an unpredictable manner. Sometimes it could be high, sometimes it could be low. So to avoid that, the designers modified the SR flip-flop and created a new one known as a JK flip-flop. And the JK flip-flop resolves the issue by simply toggling the output. Every time both inputs are high, the output simply toggles in value. And that is noted right here. At the bottom of this truth table, okay, bottom of this truth table, when both inputs are high, the output simply toggles in value. Okay. So let's explain. A JK flip-flop is similar to an SR flip-flop or an RS flip-flop. Both inputs high, output toggles in value. Meaning if the output was 1, it would toggle and go to 0. If the output was 0 previously, it would toggle and go to 1. So it'll keep toggling between the two states. Everything else remains the same. So let's take it from the top now. What do we see? There's a clock. The clock is negative edge triggered because of this bubble. So negative edge triggered. Okay, negative edge triggered. So every falling edge indicated by these down arrows, the output would be activated. For all other values of the clock, meaning whether the clock is 0, whether the clock is 1, it doesn't matter what the inputs are, the output remains in the previous state. And hence, if it remains in the previous state, meaning Q n minus 1, we say that the state has memory, or the output has memory. Memory, because it doesn't matter what the input is. The input could be changing, could have any values. It does not matter. The output will not change until the clock has a negative edge or a falling edge. Let's take a pause. Let me know if you have any questions. Any questions at all? Okay. All right. So then the actual truth table for the falling edge, we have 2 inputs, 4 options, 0, 0, 0, 1, 1, 0, and 1, 1. From the SR flip-flop, we know that if both inputs are 0, nothing happens to the output. Output remains Q n minus 1. Again, we call that state as having memory. So the first 3 are kind of related. If the clock does not have a negative edge, then the flip-flop is not responding, output stays the same. Now, if a negative edge arrives and both inputs are 0 and 0, then the output still remains in the previous state. So those 3 are said to have memory. As long as power is applied to that flip-flop, meaning it has voltage and current coming in, the output remains in the previous state. So memory. And the output only changes when J and K are 0 and 1, and 1 and 0. Similar to the set and reset flip-flop, J and K flip-flop, it should actually be R and S, because J acts like the reset switch and K acts like the set switch. Oh, sorry, the other way around. J is the K is the reset. I was correct the first time. Sorry, I'm confusing myself and the students. I was correct the first time. J is the set and K is the reset. Okay, so when J is 0, output goes to 0. When J is 1, output goes to 1. hence set reset right here. Okay, and then of course it resolves the issue when both values are high. If both values are high, the output simply toggles. Previous state was 0, output goes to 1. If the previous state was 1, output goes to 0. Hence toggle. All right, questions? Any questions? Okay. From this, we also developed another flip-flop known as a T flip-flop. A T flip-flop. Okay. T stands for toggle. So JK flip-flop with J is equal to 1 and K is equal to 1 gives us a toggle flip-flop, or more commonly known as a T flip-flop. I'll go back to the other slides afterwards, but I wanted to cover the T flip-flop. Okay, T flip-flop. So you take the JK flip-flop, you tie both inputs together to logic high, and as we just saw earlier in the previous slide, if J and K are both 1, then when the clock arrives, output simply toggles 1 0 0 1 0 1 0 1. So that flip-flop is known as a toggle flip-flop, and it's simply noted so you got J, you got K connected together to logic high, and then the clock signal C is coming in, and output is Q. Well, in this case, the output Q would be called as T, toggle. Output toggle. So that's the T flip-flop. And T flip-flops are the basic building blocks of digital counters. Digital counters. Okay. Q will simply go from 0 to 1 and 1 to 0. Okay. So a digital counter is comprised of T flip-flops. Here is a 3-bit counter. They're all connected in, the outputs are taken in parallel. Okay, outputs are taken in parallel. So it's a 3-bit counter, meaning there are 3 outputs, Q0, Q1, and Q2. So the truth table would look like this. You have Q2, Q1, and Q0. Q0 is the least significant bit, the far right. Q2 is the most significant bit. Okay. The truth table on the next timing diagram on the next page, so we'll do that. All right. So just look at the construction before I go to the timing diagram on the next slide. All of the inputs for all 3 flip-flops are connected together. So you got JK, JK, all connected logic high, right? All JK inputs are connected to logic high, indicated by that shaded dot. Okay, there's a connection there. So there's a connection here, 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 here. All other places, it's simply crossing over. Then look at the first flip-flop. The first flip-flop has a clock input right here. Then the output of the first flip-flop goes and connects or acts as the clock to the second one. In this case, we refer to the clock as the input because the J and K inputs are permanently connected and tied to 1. Okay, so J and K inputs are permanently connected to 1. So we refer to the clock signal as the input to this toggle or T flip-flop. Because the only thing that the flip-flop is doing is changing the output value from 0 to 1 and 1 to 0 based on when the clock signal arrives. Okay, that is the actual input that flip-flop. And so output Q0 goes to the clock of second one, and output Q1 goes to clock of the third one. So flip-flops 1 and 2, let's call this flip-flop 0, this is 1, and this is 2. Flip-flops 1 and 2 do not change values until the previous flip-flop output changes. And then when we look at the timing diagram, it will make more sense. Okay. So here is the input signal. This is the input to flip-flop 0. Okay, flip-flop 0. And this, of course, Q0, Q1, Q2. Q0 is input to flip-flop 1, and Q1 is input to flip-flop 2. Okay. Don't worry about these numbers at the bottom. I'll explain that at the end. Let's look at the timing diagram first. We know that these are all negative edge triggered, meaning when the clock is 0 or when the clock is 1, there will not be any response from the flip-flops. It will only respond for a negative going edge. So if we mark and note all the negative edges, the first thing to do is here in the clock signal. So the output Q0 will only change for the negative going edge of the clock input. And that's it. Q0 initial state we'll assume was 0. Then it goes to 1, right? It changes value when the negative edge arrives. So it goes to 1. Then it stays at 1 for this entire length until the next or the second negative edge arrives. That's when it will change its value from 1 to 0. So it goes from 1 to 0. It will stay at 0 until the next negative edge arrives, which is right here. And then it toggles its value, goes from 0 to 1, which is right there. And then it will stay at 1 until the next negative edge arrives, and then changes its value and goes from 1 to 0, and then so on and so forth. Okay, it changes value only for a negative edge. And the resulting waveform has a frequency that is half the frequency of the clock signal. So if the clock signal is 1 kilohertz, as was in the lab, then the output of that first flip-flop 1, sorry, not flip-flop 1, output of the first flip-flop flip-flop 0, Q0, will have a frequency of 500 hertz. So as an example, clock signal going as input to to flip-flop 0 is 1 kilohertz or 1000 hertz. Then for flip-flop 0, the output will have a frequency of 500 hertz. It'll be half, right? Pulse with this now twice. So the frequency is half. Let's take a pause. Let me know if you have any questions. Does everyone see that? Right. Then flip-flop 0 output is going, these are inputs 2, flip-flop 0, 1, and 2. Q0 goes as input to flip-flop 1. So at every negative edge, the value of this flip-flop changes from the first negative edge, which is right here. The value changes from 0 to 1. It stays at 1 until the next negative edge arrives, and then the value goes to 0. It stays at 0 until the next negative edge arrives, and the value then goes from 0 to 1. It stays at 1 until the final negative edge arrives, and then goes to 0. So for flip-flop 1, the output is half of flip-flop 0, so you get 250 hertz. Does that make sense? Right? And then same thing for flip-flop 2. It changes only when Q1 changes. And so the output of flip-flop 2 will have 125 hertz. Any questions from anyone? Any questions? Excuse me. So now let's take a look at the outputs collectively in parallel. Q2, Q1, and Q0. So you'd read backwards in this direction, right? Q2 is the most significant bit. Q0 is the least significant bit. And hence, starting from the left to the right, it goes Q2, Q1, and Q0. And if we read the outputs, we get 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 3, 4. Too much of a rush. 0 and 1, 1. Corresponds to decimal 0 through 7. 8 different states. We always start with the 0. So 8 possible outputs, 0 through 7. A 4-bit counter, like the one we used in the lab, would go from 0 to 15. Hexadecimal 0 through 15. 16 possible states, 0 through F. Okay, 16 states. And you can see the output follows a sequence. The system actually follows a sequence, the effects of which are similar to a ripple. And hence, this is also known as a ripple counter. Okay, ripple counter. All right, questions? Let's take a break. And after the break, we'll cover shift registers, and then the chapter will be at an end. So it's 10:56 right now. Let's meet back at 10:02, 11:02, 11:03, approximately 6 or 7 minutes.